Hello and welcome again. This time with more examples for molecular vibrations. Again, Saurabh Bhaktibud, your instructor here. I'm taking a typical case for your pursuit. I'll take the example of 1,2-dichloroethene that belongs to a C2H geometry. This has a flat structure as you can see here. There are 6 atoms, 2 hydrogens, 2 chlorines, and 2 carbon. And the order of the group for this particular molecule is 4 as identity C2 sigma H and the center of symmetry. So, what is unique or what is typical about that molecule that we are going to see? If we try to find out how many symmetry or element operations are there, and if you want to calculate number of unshifted atoms, then we'll do as we did in earlier case. If we talk about identity, contribution for unshifted atoms is always 3. So, and number of unshifted atoms are 6, as you can see here. Therefore, the total of 18 are the contribution of character for identity. Coming to C2, the contribution for C2 is 2 cos 180 degree plus 1, that must be equal to minus 1, because all atoms would be getting shifted as the C2 axis is perpendicular to this plane here, and this will allow this complete unit to move. So this Cl would move completely and it would come to this position, and along with it the hydrogens would move and the carbon atoms would also move. So the number of unshifted oxygen atoms would be 0. That would correspond for the 0 character. If we talk about center of symmetry, now if you are using this as a center of symmetry, this carbon and this carbon are getting reflected. This chlorine and this chlorine would be getting exchanged, and similarly this hydrogen would be exchanged by this hydrogen. So there is no atom that I would say all atoms are shifted, and therefore the unshifted atom is only 0, and whatever it would be the contribution, it would fall to 0. For sigma, because this is a molecular plane kind of thing, perpendicular to C2 axis, all 6 atoms would be there. Contribution is 1, so the net contribution would be 6. So 8006 makes a total contribution for that particular character table. Now again refer to the character table of point C2H. Once you do it, you just find out that 18006 does not belong to any of the species, either AG, BG, AU or BU. You know that all of them are one-dimensional irreducible representations. Now the next job is to decompose it using the standard reduction formula, and you know the standard reduction formula is a very convenient method of showing that reducible components can be added in terms of irreducible components using this expression that we have described in earlier lectures also. So if we go for this decomposition this way, you will find that we can simply multiply the components. Say if we wish to say how many times the Ag has come into the expression now, so you will say that 18 into 1 character of identity into the character of the identity for the other operation for these two series of operations, this and this for reducible. If you're taking a reducible in AG, then you will need to multiply these components for respective material operations, and their characters would be multiplied, and then it would give some result. If I wish to say how many times Ag has come into the expression, I'll have 1 by 4, 18 into 1 plus 0 because there are 2 zeros, so whatever is there is no need to talk about. And the last thing is 6 into 1, that is 6. So that makes it total of 18 plus 6 by 4. That is the expression is 6. How many times Bg has appeared? So 18, 1 by 4 is there. 18 into 1 is 18. 0, 0 has no meaning. 6 also is now, this time 6 is negative. 6 into minus 1, that is equal to minus 6. So your expression would be equal to 18 minus 6 upon 4, that is 12 by 4, that is equal to 3. If we talk about AU, again, so AU 18, 0 and 0 would make no sense. 6 into minus 1, so again that would be equal to 3. And BU, the 18 and 0, 0 again no meaning, plus 6, it will be 18 plus 6 is 24, 24 by 4 would be equal to 6. So your final expression is AG has appeared 6 times, BG for 3, AU for 3 and BU for 6. The total, the expression now of ours comes out to be, using this expression would be a different thing, and that will see character table for point of C2H. This is the expression 6Ag plus 3Bg plus 3Au plus 6Bu. Now what next? The next thing is that we are supposed to observe is that these are the constituents of the total fundamental modes of vibrations. Now, if you want to identify the tau reducible and we have got a result for tau reducible, then we need to subtract the rotational and translational degrees of freedom from that expression. Now, what unique feature of this particular point group is, and one must be always cautious about this, I have given danger mark for that, that Rx and Ry belong to BG symmetry because they are not shown in bracket, because they are not shown in parenthesis. So I will take an account of BG twice. So here AG once and BG twice. The same practice I would also do for the translational degree of freedom as well. So you just look at here. X and Y have not been shown into brackets. They are not shown in parentheses. So J is of course the translational motion, and 2 times BU would be your answer. So AU plus 2BU would be your answer for this. And now since our final answer is this, you need to subtract what we have obtained from our results. So the tau reducible is equal to vibrational plus tau rotational plus tau translational, that is 6Ag plus this plus this plus this plus this. And now we need to subtract the various values that we have examined, that is Ag and 2Bg. Now this is something where we need to be cautious, and similarly Au minus again now, so it is 2Bu. Now if you do it, then only will reach to some powerful conclusion. Your answer is 5Ag plus Bg plus 2AU plus 4BU and so on. So that makes it the thing. The final expression is 5AG plus BG plus 2AU plus 4BU. Just calculate how many fundamental modes of vibration are there, because all of them are one dimensional. So it is 5 plus 1, 6, 6 plus 2 is 8, 8 plus 4 would be 12. Now since there are 6 atoms, so 3n minus 6, 6 is 18 minus 6, that is 12. So yes, it is matching to what we believe to be there. Just look at this, 6 into 3 minus 6, that is 12. 18 minus 6 must be the 12th. So now we need to see whether they belongs to one of the Cartesian coordinate systems or binary products for predicting IR and Raman active vibration. Again, we'll have to follow the same rule. The dipole moment factors have the same symmetry properties as the Cartesian coordinate x, y, z. And for Raman activity, what we need to say is the polarizability has the same symmetry properties as the quadratic function or the binary product that is seen in the character table. So once we do it, then prediction from the character table would be quite easier. We find that there are 5 AG, 1 BG, 2 AU and 4 BU type of vibrations, and go from the character table and just infer something, which of them are IR active and which of them are Raman active. So if you see that Z AU, it must be IR active, X and Y BU, it must be IR active, AG and BG are IR inactive. And here we find that binary product is only for AG and BG, so they are only Raman active, because RX, because here is no X, Y or Z, so they are not IR active. Two things are the IR active vibrations, because there would be change in dipole moment of the molecule along the XYZ coordinate, and in some cases you will see that the Raman active vibrations would be observed. Just look at this. There are two binary products of AG and BG, both have this phenomena, and therefore they must be the Raman active. So the net conclusion that out of 4 kind of things that we have representation, we have that AG is IR inactive but Raman active, BG is IR inactive but Raman active, and rest of the 2 are IR active but Raman inactive. So this is how we conclude from our entire expression. Thanks for watching. See you in the next video. Thank you again.